Okay, hi, Sam Francis. This is the CLT adhesives test in support of mass timber buildings, and I suppose we could say in support of the tall wood building ad hoc work on mass timber buildings. There we go. While we don't have NCSEA credit, we do have AIA and ICC. There's information about AIA if you're looking for that. I apologize that this is the screen's not changing as rapidly as we'd like. I'm having technical difficulties. Some of you knew that. That's been going on a long time. Okay, so this course is going to talk about adhesive bonding of wood laminations, which permits the manufacture of large wood members. You can read the description there. You know that this has been going on literally for centuries. The glue laminated timbers go way back, and for that matter, things like plywood. This is a different type, and so among the things that we want to cover as a learning objective, what is cross-laminated timber and how is it different from or like other glued laminated products? What have you done to examine its properties? That would be compartment testing. We're going to talk about the compartment tests that have been done by AWC, by others going back quite a ways, actually. There are adhesive qualification tests, and ultimately that was the goal of all of this, was to come up with a qualification for adhesives to be used in mass timber buildings. And then ultimately there will be some discussion of the Tall Wood Building Ad Hoc Committee's proposed tall wood language. And before we get underway, we'd like to know more about who you are. So Marcy, let's quiz them, see if they know who they are.
Absolutely. So this one's pretty self-explanatory. Just tell us who you are and what you do. Go ahead. As usual, I give you about 30 seconds or wait until about 80% of you have voted. And we're getting real close to that mark, so I'm going to go ahead and close. And let's see, we've got 69% engineers, 16% building code officials, 3% fire code officials, 7% other, and 5% architects. No matter what your profession, we're very happy that you're here and hope that you find something useful today, and welcome. Back to you, Sam.
Yeah, sorry, I was I was muted. Okay, so here's what we're going to try to accomplish. The outline of this program, we're going to discuss what is CLT, because we're focused on primarily here cross-laminated timber. We're going to talk about the compartment tests that have been done, just exploring it, and in support of the Tall Wood Building Ad Hoc. We're going to look at adhesive qualification tests and ultimately the applicable code requirements that exist or are being proposed by the Tall Wood Building Ad Hoc Committee. So the concept of cross-laminated timber is simple. Dimension lumber laid up in layers orthogonal to one another, resulting in a large panel product of pretty hefty dimension. possible. Typical is 3 to 7 layers, which means that we'll talk about that in a moment. But that can be 4 to a foot thick, and depending on the manufacturer, it can be 11 or 12 feet wide, 65 to perhaps 80 feet long, depending on who's making it. By the way, having said those dimensions, just remember, okay, after you make this stuff, you got to ship it someplace. So did you really want to make one 85 feet long? The concept of CLT, this is new in building material terms. After all, the research isn't that old. In the 1970s, the first patent in 1985, the first project in 1993, and like any other material, utilization, selling the product, results in improved technology. So improved press technology occurred, and by the early 2000s, this was an important material advance, and the Europeans took advantage of it. It's primarily driven, as you see here, by the green building movement, and that's because of carbon sequestration. And in Europe, the so-called cap and trade on carbon is a big motivator. It costs you money if your green footprint is not good. So anyway, cross-laminated timber. First, let's a quick refresher: glue-lam beams. Again, dimension lumber laid up all in the same axis, adhered together, various properties adjusted. For example, if you want more fire resistance, you may add more strength in the tension lams and so forth. So cross-laminated timber is different in the sense that in this illustration, the top layer, the dimension lumber, is oriented parallel to the major axis. The next lam down, that layer is oriented to the minor axis. And what's different about the two? Well, CLT has 2 axes, a major and a minor, and they have to be accounted for. The components of CLT are essentially a lamination. That's a piece of dimension lumber laid next to its neighbor, which is a similar dimension lumber. And in the PRG 320 standard, the mechanical properties of those are accounted for. That's what dictates the properties of the CLT panel. A layer is a one or more laminations in the same plane of the same species and grade and thickness, so that we might have 2 layers of this 2x material here with their dimension running parallel to the major axis. Those two laminations together would be a single layer. And the definition of CLT consists of at least 3 layers with structural adhesives oriented in orthogonal layers. Okay, so that brings us to a polling question. Marcy, please.
Which of the following is true regarding CLT? All laminations within a single layer are parallel. Alternating layers are perpendicular. There is a major and minor axis, or all of the above. We need a little Jeopardy music here. All right, I've got 30 seconds, so I'm going to go ahead and close. And 79%, so that's close enough. And let's see, 89% say all of the above with just a smattering for each of the others. So I'm going to have you tell us the real answer. Actually, I think we're going to go back to Jason here. So.
Yep. Thank you, Marcy. And yeah, I'll go ahead and answer that. The correct answer is all of the above. So most people did get it right. And within CLT, it is true that all laminations within a single layer are parallel. The alternating layers are perpendicular to each other, and then there's a major and minor axis as well. So starting on the second portion out of the 4 segments in this webinar here, I'm going to talk about the compartment tests, or some of the compartment tests that have been done. In a webinar that we presented last week, we spoke about the various fire tests that have been performed in order to guide and inform code development for tall mass timber buildings. The objective of this code development activity is to ensure safe construction practices and safe design for tall mass timber buildings. Many of these fire tests have been what are referred to as compartment fire tests. A compartment fire test is one that is performed within a compartment that has at least one opening. These tests simulate a natural fire within an enclosed or sometimes a partially enclosed area, such as a room or apartment. As such, the fuel load used for compartment fire tests often consists of real furnishings and other contents that would be typical of the simulated occupancy. For example, Group R or residential occupancy. Other fuel types are sometimes used though, such as wood cribs or gas, either in addition to or as an alternative to the real furnishings. The fire growth phases of a typical compartment fire may be characterized by the time temperature diagram that's shown on the upper left corner of this slide. You may recall this slide from last week's webinar as well. We just wanted to recap on the differences here because it's important to remember the differences between a standard E119 fire versus a compartment fire. At first, they're usually the compartment fire is usually slower to develop at first, but then once it reaches a point called flashover, which is marked on this figure in the upper left corner there, it quickly grows to a very high temperature. And flashover, by the way, is the point at which all exposed combustible surfaces within the compartment suddenly become involved in the fire. That's the general definition of it. There are laboratory definitions, of course, which are more specific. This begins what is called the fully developed phase of the fire, in which temperatures are often in the range of 1,800 to 2,200 degrees Fahrenheit, or 1,000 to 1,200 degrees centigrade. Once the combustible contents within the compartment have been mostly consumed, the fully developed phase ends and the temperature starts to drop. This marks the beginning of the decay phase, which is also marked here on this figure. Barring any fire regrowth, which might result from the introduction or involvement of new fuel, the fire will eventually extinguish due to lack of fuel. By comparison, the standard E119 fire curve exposure grows fairly rapidly at first, but then it levels off to a certain extent shortly into the test. And as such, the standard E119 exposure does not reach the same level as the typical peak temperature in a compartment fire until more than 4 hours into the test. So way beyond the time of a typical compartment test. Well, actually, several compartment tests that we've been involved in have gone to 4 hours. But of course, by that time, most natural compartment fires would have cooled because they would have already consumed the available fuel within the compartment. In 2017, the Fire Protection Research Foundation, which is part of the National Fire Protection Association, commissioned a series of 6 compartment fire tests. I spoke a little bit about this test series in a webinar last week, but I'm going to delve into them more deeply in this webinar because it's of greater importance to the topic of this webinar. The tests were done for NFPA's Property Insurance Research Group, or PIRG, and the purpose of this test series was to collect data for the contribution of CLT elements to compartment fires for the purpose of insurance modeling. Testing was performed by the National Research Council of Canada, and it was performed at the National Institute of Standards and Technology Fire Lab in Gaithersburg, Maryland. All 6 of the compartment tests were constructed of CLT and all had the same overall dimensions, 15 feet wide by 30 feet deep. The opening, which was 6.5 feet tall by 6 feet wide on 4 of the compartments and 6.5 feet tall by 12 feet wide on the other 2, was situated on one of the 15-foot end walls. In 2 of the tests, all of the CLT surfaces were protected. These were considered the baseline tests because the CLT did not become involved in the fire and therefore did not contribute to the fuel load. In the other 4 tests, various CLT surfaces were exposed. Fire performance parameters such as heat release rate, temperatures, and heat flux were measured in each of these tests. The contribution of this exposed CLT was determined by subtracting the values of these parameters as measured in the corresponding baseline test. All 6 of these tests represented unlikely scenarios in which the automatic fire sprinklers, which are mandated by code, completely fail to activate and the fire service is unable to respond throughout the duration of the fire. So it represents a combination of 2 worst-case scenarios. Among the findings of this test series were that the CLT did not significantly contribute to fuel load in compartments which had gypsum wallboard on all surfaces. So in other words, all mass timber surfaces protected. In those cases, it was found that of course, the CLT or the mass timber did not contribute. And for the test in which certain CLT surfaces were left exposed or unprotected, the CLT contribution, of course, increased with increasing exposed surface area. As I noted in last week's webinar, the degree to which the CLT contributed was modeled by the Research Institute of Sweden, or RISE, in advance of the test. And the actual test results in terms of heat release rate and temperature were very close to the model predictions. So the contribution of exposed CLT in a compartment fire can be accurately modeled, and that it was confirmed that that is the case. In addition to the findings that I just mentioned, though, fire regrowth was observed in 3 of the 6 FPRF tests. By the term fire regrowth, I'm referring to a behavior in which the fire, after having cooled significantly during the decay phase, starts to re-intensify again. In each of these cases, the observed fire regrowth coincided with the failure of an adhesive bond line between the layers of CLT. Based on the data from the thermocouples that were embedded within the CLT at depths corresponding to the bond lines, it was apparent that failures were occurring before the char front reached the bond lines. This is what we call heat delamination. Before I go on to the next slide, I wanted to point out in these 2 photos here at the bottom of this slide, they were both from FPRF test 1-4. The one on the left was taken about 2 hours into the test, and that was well into the decay phase. As you can see, the fire was not very intense at this point because most of the combustible contents had been consumed and the exposed CLT was insulated with a layer of char. One might expect that the fire would slowly continue to cool from this point and eventually self-extinguish due to insufficient remaining fuel. But if you look at the photo on the right, you can see that this is not what happened in this particular test. The photo on the right was actually taken 1/2 hour into the 1/2 hour after this photo here on the left, and yet the fire had regrown to the point of a second flashover. So let's focus on that test 1-4 in particular. I'll just refer to it from here on out as FPRF test 4, just for simplicity's sake. Remember that this is the test that we showed were shown at the bottom of the last slide, and in that test, the entire CLT ceiling was exposed. This compartment had an opening size of 6.5 feet high by 6 feet wide, which was the smaller of the 2 opening sizes tested in that series, in the FPRF series. The comparative baseline for test 4 was test 1-1. Test 1-1 was the same as test 4 in every way, except that it did not have an exposed CLT ceiling. Thus, there was no contribution or involvement of mass timber elements in test 1-1. So by subtracting the measured parameters of test 1 from those of test 4, it was possible to directly determine the effects of the exposed CLT ceiling in this configuration. For example, the graph on this slide here shows that the measured heat release rate of the baseline test, which is the red curve. It also shows the measured heat release rate of test 4, which is the light blue curve, and it shows the difference between the two, which is the magenta curve. These indicate the magenta curve indicates the contribution of the exposed CLT throughout the course of the 2-hour and 40-minute test. You can see that there are two distinctive humps or peaks on this magenta curve. The first one started around 50 minutes and it ended at around 80 minutes. The second hump started around 150 minutes and continued for the next 10 minutes until the end of the test. The start of these humps corresponded with heat delaminations that occurred in the first and second bond lines respectively. The heat delamination of the first bond line occurred around 50 minutes, and then the one in the second bond line occurred around 150 minutes. So the result of the first heat delamination was simply an extension of the fully developed phase. You can see that comparing the red line to the blue line here. This is the fully developed phase for the test 4 here, and it was extended. The result of the second heat delamination, or the heat delamination of the second bond line, was a fire regrowth near the end of the test, leading to a second flashover. Okay, let's watch a video here. This is a video of FPRF test 4. And like I said, this test lasted for 2 hours and 40 minutes, but this video is greatly accelerated so that it's compressed into approximately 2-minute length here. Once again, these tests were performed at NIST. And remember that this is the test that had the exposed CLT ceiling. So there's flashover. It occurred right around 12 minutes. And this is the fully developed phase. I'm not sure if you can read the clock that is near the opening of the compartment, but it's just to the right on the ground there. We're at about a half an hour here. Now we skipped forward to about an hour and 25 minutes, and we're entering the decay phase here. So this is where the cooling takes place as the combustible contents become mostly consumed. You can see that they're reduced to basically just embers on the floor there now. Unfortunately, you cannot see in this video, you can't see the CLT, but it would have a layer of protective char on it at this point, which helps to prevent fire regrowth. But coming up soon here is the start of that the heat delamination of the second bond line, which I told you about, and the resulting fire regrowth, which is we're approaching now on this video. And that fire regrowth eventually led to a second flashover. We're at 2.5 hours here. And then they extinguish the test, or they terminate the test at 2 hours and 40 minutes there, approximately. Now, the video that we just saw was Like I said, it was FPRF test 4, but the fire regrowth behavior was also observed in other FPRF compartment tests in which there were exposed areas of CLT, either on the ceiling or on the walls. In all of these cases, it appeared that the fire regrowth was caused by a heat delamination of an adhesive bond line within the CLT. Of course, the implication of this observed behavior is that in rare instances, such as the scenarios that are represented by this test series, a fire may not necessarily burn out on its own. In other words, it may not self-extinguish even after the furniture and other contents are consumed. One example of another FPRF test in which fire regrowth occurred is shown in this photo. This was taken about 4 hours into test 3, FPRF test 3, which had an exposed CLT wall. You can see some flaming on the exposed CLT wall in this photo here. Earlier in the decay phase of this test, there was an extended period without flaming on the wall and very low heat release rate. Here again, this fire regrowth was a result of a heat delamination that occurred in one of the bond lines. However, it should be noted that in this test, the fire regrowth was not nearly as intense. It did not result in a second flashover, and the compartment eventually cooled down again on its own. But of course, as we saw in test 1-4, that's not always the case. Okay, Marcy, would you ask the third point?
In the FPRF compartment tests, all instances of fire regrowth were caused by adhesive heat delamination. Is that true or false? And our learners are right on top of things here, so we've got people, we've got about 70% have voted. I've got about 10 more seconds. All right, I'm going to go ahead and close. And we've got 89% have voted true and 11% false. And Jason, I'm going to let you say what the correct answer is.
Okay, yeah, that's good. Again, most people got it right. It is true that in the FPRF compartment test series, all of the instances of fire regrowth were caused by adhesive heat delamination, and they were directly linked to it. So moving on to the third segment of today's webinar, we're going to learn about a couple of different adhesive qualification tests that are used and how they were developed. But first, I wanted to speak briefly about a part of the impetus behind the development of these adhesive qualification tests. Specifically, I'm referring to the direction that was provided by the ICC Ad Hoc Committee on Tall Wood Buildings. So I'm going to ask Sam if he would talk a little bit about that.
My slide 24 includes the position of the ICC Tall Wood Building Ad Hoc Committee. So you're seeing a slide that shows solid wood with a char layer. The important parts of that illustration are that wood chars at a predictable, steady rate, that the char insulates the wood, and in that illustration, you'll notice that the unheated center core maintains its mechanical properties, strength, stiffness, etc. And so the performance, both structural and fire performance of wood, is predictable. The position of the ad hoc committee was great, but if you have fire regrowth, or if you have delamination because adhesives behave differently than straight solid sawn material, what happens? And the position of the ad hoc was actually to draft code language. So Jason, if you would advance to slide 25. The ad hoc, there were 4 working groups, including one on fire, and that fire work group identified the need to develop a test protocol. Actually, that group developed language that requires fire performance and of CLT, and it requires labeling of the CLT reflecting that performance, which can be interpreted to be a protocol for heat delaminating adhesives. There are actually two things going on here. One is delamination, the other is fire regrowth, and it was the ad hoc's position that both needed to be identified, and the acceptable performance required by some protocol. So if you'll give me slide 26, then I'll let Jason pick up again with the testing that begun at Southwest Research.
Okay, great. Thank you, Sam. So based on the direction provided by the ICC TWB Ad Hoc Committee that Sam just mentioned, in the fall of 2017, AWC commissioned Southwest Research Institute to develop a test protocol which would be capable of distinguishing between adhesives that can lead to fire regrowth versus those that do not. Specifically, there was interest in replicating the severe exposure conditions of the FPRF compartment test series to determine whether or not the same fire regrowth behavior would have been observed if the FPRF test had been performed using CLT products made with other adhesives. In order to determine this, it was necessary to replicate many of the aspects of the FPRF compartment tests. For example, a large-scale compartment test was used rather than a small or intermediate scale compartment, and the aspect ratio of the compartment footprint was about the same, about 2:1 depth to width ratio. Also, the compartments were constructed to have the same ventilation ratio as that of the FPRF tests, having a small opening, which was about 0.03 meters to the 0.5. So I will note that this compartment size was not exactly the same size. It was smaller than what was used in the FPRF test series. However, it's large for a standardized test, and it also had the same, like I said, same aspect ratio, same ventilation ratio. In this test procedure, the CLT sealing is left exposed, similar to the configuration that was tested in FPRF test 4. And the CLT sealing is loaded to the same uniform load, and the span of the sealing was about the same, or it was exactly the same, 15 feet, which is the same span that was used in FPRF tests. As for the exposure, the gas burners within the test compartment were calibrated to replicate the exposure conditions measured in one of the FPRF baseline tests, which was test 1, FPRF test 1-1. This was the baseline test that had the small opening, as you recall, the 6.5 foot high by 6 foot wide opening. This exposure replication was based on the measured heat flux near the sealing in the FPRF test. The graph on the left shows temperatures that were measured on one of the thermocouple trees in the FPRF test 1-1 with respect to time. And then the graph on the right shows temperatures that were measured in the large-scale compartment test calibration performed at Southwest. Note that the time temperature curves are similar. They're not exactly the same, but that's because, as I just mentioned, this replication was based on heat flux to the sealing rather than temperature. So it's really based on exposure to the CLT. The discontinuities or apparent steps in this graph, the graph on the right that is, are a result of the fact that the gas flow rate followed a step function rather than a continuous curve. But the heat flux to the sealing at any given time, and more importantly, the cumulative heat flux to the sealing throughout the test, were very close to the measured values in FPRF test 1. So the calibration test confirmed that it was possible to replicate the conditions of FPRF baseline test 1. However, it was still necessary to validate the test protocol by testing the same CLT that was used in the FPRF test series. As I noted previously, this test protocol involves an exposed CLT sealing, which is the same condition that was tested in FPRF test 4. So it follows that the test protocol would be considered valid if the test performed on the same CLT that was used in the FPRF tests resulted in the same behavior that was measured in that test. These are some of the photos of the validation test that was performed at Southwest. The photo on the left was taken at about 10.5 minutes just prior to flashover. You can still somewhat make out the exposed CLT sealing because at this point it had not yet ignited. And then the photo on the right was taken just after flashover, about 14 minutes after the start of the test. Here are two photos from the fully developed stage of the validation test. The one on the left was taken near the beginning of the fully developed phase, about 15 minutes. And if you're wondering what was causing that little bit of flaming on the floor near the opening, that was actually just the gypsum wallboard facing paper. The lab placed that there to protect the concrete floor from the fire. And then the photo on the right was taken at about 1 hour, which was about 2/3 of the way through the fully developed phase. It was right around this time that the first bond line started to undergo heat delamination. This corresponded also closely with the performance that was observed in FPRF test 4 at this stage. On this slide, the photo on the left shows you a visual of the conditions within the test compartment during the decay phase. This photo was taken about 3 hours into the test, and it was just before the fire regrowth started. The photo on the right was taken about 12 minutes after the one on the left, at about 3 hours and 10 minutes. You can see that there was indeed significant fire regrowth leading to a second flashover. And this fire regrowth here again, just like in the FPRF tests, was caused by the delamination of the second bond line in the exposed CLT sealing. Let's watch a video of that one now. Again, this is the validation test of the adhesive qualification procedure or protocol that was developed at Southwest Research Institute. And this was a 3 hour and 11-minute test. It's compressed into about a 2-minute time frame again. So it's we have some times here when it's played very quickly. It's slowed down at this point because this is the flashover here, about 13 or 14 minutes. And this is the fully developed phase. We just skipped ahead to 38 minutes there. Still in the fully developed phase at this point. Now we're past 1 hour. And this is past 2 hours now in the decay phase. You can see that for the most part, there's a protective layer of char over the entire ceiling. However, you do see some flare-ups that are occurring there, some fire regrowth. Now we're getting into the point where the major fire regrowth, the significant fire regrowth, started to occur just past the 3 hour mark, and it did result in a second flashover, which you can see there. By the way, the inset there is the ceiling. You probably figured that out already. That's the black and white image in the top left. And then the test was terminated at about 3 hours and 11 minutes here. Here are the measured time temperature curves from the 4 different compartment tests that we've talked about so far. The 2 graphs on the left are from the FPRF tests, while the 2 on the right are from the tests that were performed at Southwest Research Institute. The time temperature curve of the validation test that we just saw in the video is shown in the lower right, and then the curve of the FPRF test 4, which we saw in the first video, is shown in the lower left. The graphs at the top are from the tests performed without any exposed CLT, so they're like the baseline tests, while the ones on the bottom are from the compartments that had exposed CLT on the ceilings. As you can see, there are similar differences between the graphs on the top versus the respective graphs on the bottom. This indication of how the exposed CLT affected the temperatures within the compartments was consistent between the 2 test series. Now let's just look at the two tests in which there was an exposed CLT sealing. A comparison of the temperatures at the sealing reveals that during the decay phase, just prior to the fire regrowth, temperatures were about 450 degrees Celsius. This was the case for both the FPRF test and the validation test that was performed at Southwest. The measured temperatures from the two tests were also consistent with each other at the end of the test, at the end of each test during the fire regrowth stage. In both tests, the measured temperatures were right around 800 degrees Celsius at this stage, near the end of the test. This provides conclusive validation of the adhesive test protocol, qualification test protocol, the objective of functionally replicating the exposure conditions measured in the FPRF compartment test with a more repeatable and slightly smaller test protocol had been achieved. As I mentioned earlier, one of the reasons that that we wanted to develop this test protocol was to determine whether or not the same fire regrowth behavior would have been observed if the FPRF test had been performed using CLT products made with other adhesives. To that end, CLT products made with other adhesives were also subjected to the same exposure under this test protocol. For example, the time temperature graphs from a test performed on CLT made with melamine formaldehyde resin is shown on the lower left, and then on the lower right is a time temperature curve from test performed on CLT made with an improved formulation of polyurethane resin. So that's the improved version of polyurethane resin there. So if you inspect both of these graphs at the bottom, on the bottom of this slide, you can see that no regrowth, no fire regrowth occurred during either of these tests. This is obviously very different performance than that which was observed in the CLT made from the heat delaminating polyurethane resin. In fact, these graphs confirm that performance that is, performance that is very much in line with what would be expected from solid wood. In addition to the large-scale compartment tests that we've been looking at, there's also an additional small-scale adhesive test, which is used for CLT adhesives in North America. Specifically, I'm referring to CSA 0177, which is referenced within the PRG 320 standard, which is the product standard for CLT that's referenced in the code. So in this test, a specimen of CLT that's made with adhesive, the adhesive that's being qualified, is exposed to a Bunsen burner flame having a temperature of between 800 and 900 degrees Celsius. The exposed face of, is the edge or cross-section of the CLT such that the edges of the glue lines are directly exposed to the flame. The duration of this exposure is 10 minutes. It's 5 minutes in 2 different orientations. This photo, which was provided by the FP Innovations, shows a small-scale adhesive test being performed. So this is the CSA 0177 test as modified for CLT. Following the test, the samples are cut in half such that the cross-section of the specimen is visible. The CLT samples are then inspected for delamination using an optical comparator to measure the 5 inner bond lines for the total length of delamination. Under the acceptance criteria that are specified within this standard, the sum of the delamination of these 5 exposed bond lines shall not exceed 3 millimeters, which is a little greater or a little less than 1/8 of an inch. So that's the sum of all of these. It needs to be less than 1/8 of an inch. As such, this small-scale test distinguishes between adhesives that undergo heat delamination versus those that do not. This photo on the left is the pre-test, what the samples look like before the test, and then this is after the test here. Marcy, we have a 4th question now, polling question.
Sure, here we go. So large-scale compartment tests performed at Southwest Research Institute revealed fire regrowth was observed with tested heat delaminating PUR. No fire regrowth was observed with tested melamine formaldehyde resin, or no fire growth was observed with tested improved PUR, or all of the above. So, Go ahead and select your answer in the poll window. All right, I've got 40 seconds, so I'm going to go ahead and close. All right, Jason, we've got 80% say all of the above, 10% say fire regrowth observed with heat delaminated PUR, and just 5% for each of the others. So
right.
I'm going to let you tell us what the real answer is.
Okay, let's go with the majority, and they are correct. The answer is all of the above. Like I just reviewed there, or what I just went through, is that the heat delaminating PUR did result in fire regrowth. No fire regrowth was observed with either of the other adhesives. So it's all of the above. Last segment here, we're going to talk about the applicable code requirements that pertain to this particular topic, and that is adhesives used in CLT. Let's start with the International Building Code, IBC. I'm sure most of you are already familiar with the IBC. It's the model building code that's used as the regulatory basis throughout the US for building construction. Chapter 23 of the IBC requires that CLT be manufactured and identified in accordance with ANSI APA PRG 320. And PRG 320 is the American National Standard for performance-rated cross-laminated timber. Specifically, this requirement is given in section 2303.1.4 of the IBC. As a product standard, PRG 320 specifies a wide range of requirements for CLT used in building construction. The provisions of PRG 320 include requirements governing dimensions and tolerances, specifications and performance, qualification and marking requirements for the CLT, and quality assurance requirements. In other words, this code reference product standard is all-encompassing, and it covers every aspect of importance for CLT used in buildings in North America. But the one we're most interested in, of course, is adhesives for this particular webinar. So let's look specifically at the provisions pertaining to that. Section 6.3.1 requires compliance with ANSI 405, which specifies various types of adhesive tests, including the small-scale CSA 0177 test that I described a little earlier. So Section 6.3.1 mandates compliance with the small-scale test, but then in addition to the small-scale test, Section 6.3.3 of PRG 320 also requires that the adhesive be qualified in accordance with a new mandatory annex, Annex B, which is now part of the 2018 version of PRG 320. The test protocol described in Annex B is a large-scale compartment test that is essentially the same as the test that I just got finished describing, which was developed at Southwest Research Institute. As you'll recall, this large-scale compartment test measures fire regrowth, or more importantly, lack thereof, as the case should be. The text shown within this box here is this is an excerpt from section 6.3.3 of PRG 320-18. One of the notes, which you can see here directly below section 6.3.3, clearly states the intention of this provision. That is to identify and exclude the use of adhesives that exhibit behavior resulting in fire regrowth during the cooling phase of a fire. Here's the scoping language. I won't talk much about this because it's basically covered the section B 1.3 actually covers it's kind of a repetition of the acceptance criteria, which I'm going to talk about next, or 2 slides from now. Here's the calibration time temperature curve. Again, all of this is part of Annex B, the new Annex B, which is mandatory in PRG 320-18. This curve should look familiar to you since it's essentially the average of the measured time temperature curves from the calibration test that we talked about earlier. The laboratory performing the adhesive qualification calibrates their test apparatus by adjusting the fuel flow rate to achieve this specified time temperature curve. As we discussed earlier, this is not exactly the same as the measured time temperature curve from FPRF test 1. Rather, it represents the time temperature curve that's necessary in order to achieve the same heat flux to the ceiling as in FPRF test 1. Once the test apparatus is calibrated, an 8-foot wide by 16-foot long CLT specimen made with the adhesive that's being qualified is placed in the test compartment such that it forms an exposed ceiling within the compartment. The exposed CLT floor ceiling assembly is then loaded and subjected to the prescribed exposure, which replicates the relatively severe exposure of the FPRF test. This exposure, again, is carried out for 4 hours, 240 minutes. Here you can see another picture of the test. This is what it looks like from the during the fully developed phase at about 40 minutes. Let's talk about the acceptance criteria. The acceptance criteria for determining whether or not the adhesive qualifies for use in CLT under the IBC are given in section B12 of PRG 320. They require two things in particular. You can see that in the excerpt box here. First of all, the exposed CLT assembly must sustain the applied load throughout the entire 4-hour test. And then secondly, the temperatures measured by the 5 thermocouples at the ceiling must all remain below 510 degrees Celsius throughout the time period from 150 minutes all the way through to the end of the test. Recall that significant fire regrowth was observed in the validation test that was performed during the development of this test protocol at Southwest. And during the fire regrowth stage in that particular test, measured temperatures far exceeded this threshold, the threshold limit that's now specified in PRG 320. In fact, it was exceeded by several hundred degrees. So therefore, the adhesive that was used for the CLT that was tested in the FPRF test series would clearly fail these new requirements and would not be permitted by the code for tall mass timber buildings. In summary, these new code provisions provide the mandatory code-prescribed regulatory means of identifying and excluding adhesives that allow heat delamination leading to fire regrowth. They establish a means for ensuring that CLT used in buildings will perform like solid wood in the event of a fire. In other words, when exposed to fire, the members will undergo steady, easily modeled char development and maintain an unheated core insulated by the char layer. And then most importantly, they will not exhibit any behavior leading to fire regrowth. One more polling question, Marcy, and then I think that concludes our webinar today.
All right, we're going to do this polling question, and then I think we're going to have some questions and answers before we close out. So, which of the following standards addresses appropriate CLT adhesive performance for tall mass timber buildings? Is that APA PRG 320-2012, APA PRG 320-2015, APA PRG 320-2018, or any of the above standards are suitable? So go ahead and vote. All right, I've got about 70% and 35 seconds, so. All right, so 70% say APA PRG 320-2018, 19% say any of the above standards are suitable, and just 11% between the first two. So, Jason, what do you say?
All right, the correct answer is the 2018 version of APA PRG 320. That's the version that addresses includes the full-scale test protocol for adhesive qualification that I've been describing, and so that is the one that is appropriate for CLT adhesive performance for tall mass timber buildings. Thank you, Marcy.
Thank you, Jason and Sam. We do have a couple minutes here for some questions. So let me start it off with this one. Some folks interested in the makeup of the improved PUR. Any insight into what distinguishes that from the original one? Yeah,
sure. I'll go ahead and take a stab at that first, and then Sam can follow up. But as far as the formulation goes, that of course is proprietary. These adhesives are highly proprietary, and so we don't know exactly what the differences in the chemistry are. That's really not needed. We don't need to know that anyway, because this is based on performance rather than chemistry. So, but the bottom line is that they need to meet the requirements in terms of these new adhesive qualification tests, including the large scale and the small scale adhesive tests.
Sam, anything to add there?
That covers it all. I will say one thing not exactly added to that, and that is that the 2015 PRG 320 also had a delamination test protocol, but the Tallwood Ad Hoc Building Committee's hearings heard no one who liked it very much, even though no one brought data that said it didn't correctly discriminate. But the result of the ad hoc's efforts was the new protocol that is now Appendix B mandatory, Annex B in PRG 32018.
Great. So I know last week we talked a little bit about these unlikely scenarios, rare circumstances. These are pretty long fire tests. What are the unlikely scenarios that we're trying to cover here?
Okay, I can talk about that. Well, I mentioned in one of the slides that the reason this is representative of an unlikely scenario is because actually it represents two unlikely scenarios happening simultaneously. And those are specifically that a complete failure of the sprinkler, the automatic fire sprinkler system, which would be required by code, and then secondly, failure of the fire service to even be able to provide any intervention at all throughout the entire duration of the fire. So obviously both of those are very unlikely. It can happen though, and that's why we're testing it. But I just wanted to keep the context in everybody's minds that this is not an everyday event that's being tested here. Sam, did you have anything to add?
No, that the rare event of sprinkler failure and simultaneous fire department response that's one thing, but there are other features that the for example, workmanship of assembly that Tallwood Ad Hoc Building Committee took into consideration. It's the ultimate performance test in Appendix B looks specifically at the non-regrowth and non-delamination functions, but there are a number of things besides just the adhesive that might contribute to that long term. So our next seminar in a couple of weeks, April 5th, we're going to talk about the Tallwood Building Ad Hoc Committee's proposals, what came out of that committee, and there's a lot beyond just meet the two test protocols, CSA 0177 and Appendix B1 of PRG 320. There are other things such as how panels come together, how do you treat that, and so on.
Great. That was the next question I was going to ask you, Sam, so you read my mind. Nice trailer for our April 5th webinar.